Hi everyone, I'm Sanjit. I'm a principal DS at Verizon. And today I'm going to talk about local RAG using Embedding Gemma. So local RAG means like you can run the RAG queries or you can do like basic classification on your local machine itself. You don't need like a cloud API or anything fancy to do basic querying on your documents. And based on the size of the documents, based on the model itself, you can chunk the document and then do your local RAG. So let me just go in terms of the agenda. So I just put this into different buckets based on like, I just wanted to give an overview of like what word embeddings are and how things work and why embedding Gemma works like it is today, and then compare it to some models, Quen and the one which is available on Hugging Face. So let me just go ahead. So I think this, before the word-to-vec paper that came in 2013, it was pretty kind of, I would say, difficult to do natural language processing because you had to do like create a dictionary, then from the dictionary get to know like how you do like word vectors in terms of, I would say like you count the number of words in your document and then you do like either you do like one hot vector or those kinds of like dictionary kind of things, which is not perfect in a sense that there was no like, you can't do basic like similarities, even though similar words you see like motel and hotel, because of the one hot encoder, even if you do like basic cosine similarity, it would be like almost zero because they don't align. So in that sense, it didn't work out. And this was the first paper that came out in 2013, which kind of gave way to how you look at vectors as an embedding or as a word, as an embedding, and then you can compare things. And based on the context of the word, you could get to know what the word is, rather than like just have like a dictionary meaning of a word. Because example is like a bank could be like a bank, river bank, or it could be like a financial bank. So based on that context, this started, and this is where the word embedding started. And I just wanted to go like, the next step is like, this is how we do basic word similarity today. And this is used in every RAG system. Like when you have to basically compare the query to your document, you do basic cosine similarity, which is in terms of trigonometry is simple as like the cosine of the angle between the two word vectors, and these are in multi-dimensional space. So if they perfectly align, it would be like 1, but if they are orthogonal, it would be like 0. So in this sense, it gives you an understanding of how things are and how do you compare things. And we just use this to do any kind of, even if we have to do like any RAG or any classification, we use these kinds of techniques just to do the basic comparison between different word embeddings and their comparison. Okay. And feel free to, if you have any questions, I think this is just the basics of how things are and how the basics work. But even if you have any questions, just let me know. Yeah. And then this is where embedding Gemma starts. Like this, I'm going to talk about like why embedding Gemma is kind of does the work in terms of, it's just a 308 million parameter model, which is again trained from the Gemma 3 series, and it supports like 100 plus languages. And I'm going to talk about like why this works in terms of like how this is so powerful and like how it is able to do majority of the task with good performance. So it has like a 2000 context window token, and then it could be run within like less than 200 megabytes of RAM. So all this is kind of helping you do like on-device RAG. So if you have like, so a lot of times you would see like in your organizations, like there is like a funding for projects, but you have to do a POC. So you do a POC, you could do a POC with this, show some results, and based on that POC, you could go like use the Gemini embedding rather than this Gemma embedding. So it kind of gives you a good starting point to see and compare how your things work. And I'm going to talk about like how this is coming out to be. Like, let me just go in this part. So this is where kind of the magic is, or where they are doing all the intelligence behind the hood. So in terms of, if you see, this is coming from the Gemma 3 series. So Gemma is a decoder-only model. So first they converted into an encoder-decoder architecture, and from that encoder-decoder architecture, they pull the encoder, which gives us the embedding Gemma. And then on top of it, so there is some things like, which is called distilling of the information. So what happens is like, there is like a teacher model, which is the Gemini embeddings, and this is the student model, which is the Gemma embeddings. So what it does is, it is mimicking the vector embeddings of the teacher model, because it's like in multi-dimensional space, it's trying to mimic how the alignment is. And with the help of that, it is able to match the performance up to a certain level, because again, this is just 300 million parameters, right? And that's like billions of parameters. So this is giving you the performance, but at very low latency and low performance requirement. So that is helping it. And then there is this concept of regularizer, which is kind of, regularizer is, there is a concept called distributed embedding. So if you basically spread the embedding into a multi-dimensional space, you could either restrict it or you could spread it. So if you restrict it, sometimes it might not be robust. So these kinds of things help in the performance over multiple tasks, because I believe like a lot of parameters which they show in terms of like the performance, sometimes you also need to have like a general performance, not just performance on specific evals. So those kinds of like regularization helps. And then there is some pre-fine tuning stage, which helps again with performance on multiple tasks, because like a rack system could be used for classification, like basic information retrieval and other tasks as well. So these kinds of things help. And then model swooping is pretty much similar to how you do like an ensemble method, where in the random forest you do like voting, and then from the voting you get like a final model. So model swooping is like averaging the weights from the different models. So it's pretty much similar. So again, like in ensemble methods, because of you have like multiple things, you try to reduce the covariance. In a similar way, you are trying to improve on, okay.
Yeah, it's just timed out.
Okay. Yeah, so this is how it is performing up to that level. And then the last part, which is one of the, I think there's a different paper. So this technique is not just used by Embedding Gemma. This is also used by OpenAI and other models, because a lot of like information retrieval things happen at like, you can get like great performance at a very high level in terms of like with high performance, like in terms of high computing. But if you need something which runs locally pretty well and helps you do the downstream task pretty well, you need something like this, which is again like, which is called like the Matryoshka representation learning, which is like, if you know the Russian nesting dolls, these are like every doll is the same, but it's a smaller size. So in the same sense, like you get this this sentence, and then this is the embedding model. This is like, I'm not sure if this is visible from there, but it's like 1024. So this is your starting embedding size. But what they do is like, in the first few integers itself, they like, say suppose they would try to have most of the information in these bits rather than on the final ones. So you can truncate it, but you can still keep the performance. So this is based on that. And because of this, you have multiple embedding sizes for embedding Gemma. So you have, it goes up to 768 the maximum size, and then you can, I think, reduce, and I'll tell you like till what point you can reduce it to. So based on your performance, based on your machine, because this could run on very local machines, so you can reduce the embedding size and then still keep a certain level of performance. So this is giving you those things. And then this is, so I just wanted to do embedding Gemma versus certain other models which are available on Hugging Face. Again, all these models are available through the sentence transformers API. And these are like the parameters for those models. Like the parameter counts is 0.6, 308, and then 22.7. And I gave like, I pulled the last metric, which is the downloads last month on Hugging Face, which kind of gives us a picture of like how popular these models are. Because if you could see, like this model is like 150 million downloads last month, and those are like 4 million. So again, embedding Gemma is out there, but there is a benchmark called MTEB, which tracks the performance of embedding models. And in this, embedding Gemma is on the 10th, but if you compare it to the size of the model to the other models which are out there, it performs pretty well. And here you can see like the embedding sizes, which were like 32, 224 for the Quen model, and then similarly for embedding Gemma and the all mini LM. And here you could see like all the languages which are supported, which are pretty similar for Quen, but again, this is just primarily English. But this has the lowest context window, but mostly like when I do my work, like a lot of things could just be done with the all mini LM embedding model that is out there. Because even if you have like any call transcripts or anything, you can just segment or chunk the call transcripts into different things, and you can do your basic querying on your local machine. So this is something that I did just for this talk. So I just wanted to see like how I can compare those three models, because the last model is just 256 words. So I just looked at one document, which is the Q3 alphabet earnings call, and I just took it as a PDF. And I just segmented it into a 64-word chunk text, and then I just used, so from the whole earnings call, I could pull like 160 chunk, that is like based on the size of the earning call. And then based on that, I manually labeled things because I wanted to get the ground truth labels, and then I wanted to rank things and get some metrics which could compare the different models and see how they perform. And this is just one example. You can do you can have any local documents that you use in your work or your like academic work, and then you can just do it like in that manner. You just need to have a way to structure those documents that you have to query or you have to like parse, and then again, like you may not need like a manual label in the starting. You can just create some basic, I would say, things to start with, and then you can see, and then you can fine tune the data as well. But this is something that I created manually just to compare, because the APIs might be a little different for different models. So it's so on that, how those things are. And I just did 2 tasks on this document. I just did like a regular RAG, which is just like querying for a given. So mostly what analysts do is like they look at an earnings call and then they ask certain questions like what was the financial guidance and those kinds of things. So I just did a similar kind of a RAG, and then topic classification is like again what is a given document is covering. And I just did, for the RAG, I did using the FAISS package, which is available from Meta, which does the basic, which was I was talking about in the beginning. It does the L2 normalization, which does the cross cosine similarity, which performs a cosine similarity because you have to normalize the dot product, right? So that does that, and then I just did like a recall at 5, and then the rank metric. And then for the topic classification, I just did a logistic regression model. So this is again just a way to evaluate things and see how the different models are performing one versus the other. And this is just like, so I did some basic queries. So this is what I got from that, from those things. So say suppose what is the CAPEX guidance for 2025. So here you could see like the top response for the Quen model and the embedding Gemma are pretty similar because they are the same. And then for the all mini LM model, it's different. And this is not what it is supposed to be. So the responses for the Quen and the embedding Gemma are correct because it does cover the query pretty well because it is talking about the increase of the CAPEX from 91 billion to 93 billion. But all mini is not able to capture it in that respect. And then how is YouTube Shorts monetization progressing? So in this one, only the embedding Gemma is able to get the right result. So again, I just wanted it to be 64 words, again, because to show on the screen and to say exactly what you're getting. If I had like 256 words, maybe this was not visible on the screen. So I just made it like specific for this talk, just so that it is like visible and then you can actually see how it is performing. And these are like, based on this, these are the metrics. Like, and the higher these are, the better it is. And again, if you compare the Quen versus the embedding Gemma, even the all mini is pretty good, like in a lot of these queries. But again, like embedding Gemma is slightly better in certain things, like how is the YouTube Shorts? Because I showed, right, like only it was able to capture the YouTube Shorts question. So again, it depends. It could again depend on the query itself, how the embeddings are created, because these models are creating embeddings for both the query and the document. And then we do like cross cosine similarity using the FAISS model. So it is like how well you do the document embedding and how well you do the query embedding. So it all depends on that. And then again, it's pretty simple in a sense that you have like a benchmark or you have like a starting point. And here you could see results using publicly available data that like, and then you can do on your own local machine for your own data. So this is again like, which is something you can digest in a sense. This is not like a very like deep financial kinds of things. You can look at the results and then compare, and then you can see like how well the things are performing. And then this is results for the classification. So based on like the different, so in the earnings call, there are two sections. There is like a prepared remarks in which they talk about how things happened, and then there are like questions and answers. So I basically converted both the sections into different topics, whether it is covering AI models, it is covering like cloud infrastructure, financial guidance, and others. And then again, what I'm trying to do is like, I'm trying to see how many actual instances are able to be classified using the multinomial logistic regression model. And again, the numbers are pretty high because this is training data itself. This is not even like test data because we are not comparing how good the logistic regression model is. We are just trying to compare how good the embeddings that are generated. So our objective is not to see how good the logistic regression model is. Our objective is to basically compare the different models which we are using. And that's why, like, because mostly when you do like a real world machine learning model, like sometimes you see like 0.1, 0.2, those kinds of recall numbers. But here you see like a lot of those numbers are like higher than 0.5, 0.8, even 1, because 1 is almost like, that seems a little, because again, we are using the in training data, so it could be like an overfit as well. But again, like we are not looking at the model performance, we are trying to see how good the embeddings are and how good they relate to the topic. Yeah, so this is I don't.
Where you're comparing the couple, just the previous slide with logistic regression.
This one?
Yeah. Could you do one more column? Just suppose I don't do any embeddings and I just do a TF-IDF for the actual precise words, and just for comparison, what that would look like.
So yes, could you repeat?
So right. So here you've got 3 different inputs to a logistic regression model, right? Which are all these different embeddings. Oh, what dimensionality, by the way? I'm sorry. These are all.
So these are. Let me go back. Yeah.
I know there were options there. You picked the.
So this is the Quen. The Quen is 1024.
Okay.
The embedding Gemma is 768, and this all mini is 384.
Okay, so you picked the maximum.
Yeah. Yeah.
So, but then suppose I don't do any vector embeddings. I just take the original document word matrix.
Okay.
Maybe I TF-IDF that, just for comparison to see. How much is as far as classifications, how much are the embeddings helping me at all? Just would give you a little more of a sanity check on that.
Yeah, so you're saying like instead of like doing.
In addition to comparing these embeddings against one another, compare them against if I did no embedding whatsoever.
Got it.
Have you been using this in Verizon? Is there anything in production that's doing?
Yeah, so I use it for call transcripts. So I try to understand like when a customer calls in, I look at like device quality. So I look at like how customer is experiencing the device and what kind of an experience they are getting whenever they talk to a rep. So I use it to understand those kinds of calls using these. So I'm able to, because like the transcripts are pretty long. If you have to listen to a call, it's like 2 hours long sometimes because it's a long back and forth. So these kinds of things help me get to right to the point where the issue is and then see exactly where the customer is. Because sometimes just classification itself, like when they categorize this as like troubleshooting, this as like billing, this as payment, that doesn't give us a lot of things. So a lot of times like new devices are launched. So and then new technology is there, so those kinds of things are there.
In those call transcripts, do you measure what sort of things do you measure, like the customer's tone, semantics, things like that?
I personally don't, but some people do, like in terms of sentiment of that talk, like if a person is happy or sad or whatever, like how are they angry or those kinds of things. I mostly look at it like in terms of, because my work is related to supply chain and related to devices and their things. So I do look at like root cause analysis kind of things, those kinds of things.
No more questions, and thank you very much.